Hello everyone, in this video we want to see how we can simulate the fabric structures and minimal surfaces. First we should change the units of the rhino to centimeters. So from this tab below I click on meters and then change it to centimeters and press OK. Now we can draw a rectangle, so I can type 30 to 60 centimeter if I want these dimensions. Now I can bring it into my Grasshopper screen, and that's by bringing one curve container and set one curve. Now we have the curve and we want to make a mesh out of it. So I'm typing boundary surface. And I'm connecting this curve to the boundary surface. Next, we want to add some circles on top of this surface, so we need to extract some points from the surface, and that's by evaluating surface. So I type evaluate surface and add this surface to the S input, and I can use an MD slider to extract one point on this surface. Just it should be noticed that this MD slider is in a domain of 0 to 1. So in order to be able to select points on this surface, we need to also change the domain of the surface to 0 to 1. So that's by reparametrizing the surface. By right clicking on the surface input and click on reparameterize, we can do this. Now we can use these points as the input for this circle and define one radius for it. So I can say from 1 to 5.5, so that I can change the inputs based on these numbers that I entered. Okay, now we have the circle, and we can set where the plane or center of this circle is located on this surface. Now if we want to make a trimmed surface, we need to connect the initial surface with the only the rectangle, and adding also this circle to this boundary surface. So that's by pressing the shift. And now you see that this is a trimmed surface, so the circle part is made a hole inside the surface. Now in order to make a mesh out of it, I'm using tree remesh, and as you see again here, the trimmed surface is not considered, and the initial rectangle is used as the basis for the mesh. To solve this, we are using a mesh VREF, so I'm typing mesh VREF and selecting this surface as the input for it. So now you see that it's considering this trimmed surface. But to also make it a tree mesh or triangular mesh, I'm using the output of this mesh as the input for tree mesh, and we can adjust what is the length of our mesh. So you can see that if we increase the number, the mesh starts to not be so smooth, and you can see these edges for the circle part. And then if we make it, let's say put it on somewhere like 2 centimeters, that seems to be okay for our scale. Now we want to consider our Kangaroo setup. So we go and we consider our solver, and we can consider what are the parameters for this solver. First is the setting it on, so that's by using a boolean toggle. We put it on true, and also a bottom for resetting. Okay, now if we only consider this mesh and connect it to the goal object, it doesn't work because it's not defined as a Kangaroo object. So we need to use this show object, and then you can see that this is resulting in a Kangaroo solver result. But now we can also show other rules for setting our Kangaroo setup. and for example defining this outer line as the frame, and that's for using we can extract the naked vertices of this mesh, and so also press Alt to add space inside our screen, and so I can connect the point to the naked vertices so that you can see that only these points are selected. And now we have them, and we want to only define the outer points as the frame, as a rectangular frame for us, that these points should be kept in their place. So I'm using a dispatch component and making a dispatch of these points if they are on this rectangle or not, and that's by considering the component pointing curve. And I connect the point and connect this curve, initial curve that we had. We can double click on the wire so that we can take an extractor out of it and place it somewhere so that we know where it's connected to. And now I can see the output of this pointing curve. So you see it's shown that if it's 0, it means it's outside of these boundaries, it's 1 coincidence, and 2 means inside. So now I will make a equality function, and then I use if it's only having coincidence with this boundary. And I define the output of this equality as the pattern for the dispatch. And now if I connect one point container to the output of A, you can see that only the points on the frame are selected. And the B output is the points inside, which is the circle. And we want to define them as support points, so I go to the Kangaroo tab, and in the anchor section, in the goal points, we can find the anchor, and we define these points to be kept in their place. Now I can use a merge component to combine these goal objects. So I use the show as the second input, and define overall this merge as the goal objects. So now if I use a list item, I can only extract the mesh out of this solver, and that's by defining slider number 1 or index number 1. Okay, so now we can extract this mesh out of it, and we should define some other goals, because as you see here, it's not changing anything by resetting the solver. Okay, now we can also define the initial or the points on the boundary on the circle as also support points, and then we want to move them so that they are changing the shape of our mesh. Okay, as you see, I'm using a move, and I'm defining the z vector as the direction for the points to be moved on. And we define this as the target for these points, so they should be, and they can also be placed from 0 to 7, so we can change how they should be moved in the z direction. I press shift and also define this as the D1 in the merge, and then as you see here, if I run it, it changes the length of the mesh, and that's because we didn't set a rule for it so that it should keep the length of the mesh. So to solve this, we can go to the Kangaroo tab in the goals mesh and use this edge length, and we can connect the mesh to the mesh input of this edge length. and again pressing shift and connecting it to the first input of the merge. So now you can see that the edge length of this mesh is equalized. Also another component to keep the mesh smooth is by using this smooth component, which is like ironing the mesh, so make it more smooth. We can also connect this mesh input to the mesh input of the smooth, and also press shift and connect it to the first input of merge. Now you see that it's more smoothened. Okay, now we can also make a negative direction for our move, so that it goes down instead of going up. Or we can also set it so that it can both go up or down, and that's why double clicking on the number slider, and we can change the minimum to minus, for example, 7. So it goes from -7 to 7, and we can have both directions for the move. Now we can come back to initial setup, for example adding more circle to it, and to do so I will disable these parts because I only want the surface and the circles to be shown in here. I don't want the other parts to start running and make the computation or the running heavy. So now I add another MD slider and I place it somewhere else. I can also define another radius so that they are not the same size. So we can change the domain of the second radius as well. Okay, now if we enable the boundary surface, we can see that everything is updated, and that's the power of parametric design. So now here, if I run this solver, you can see that now this move is working for both of them. They can go together up or down. Now if we want to make one of them go up, one of the circles, and the other one go down, so make them separate or independent from each other, we should add some functions in between. So for these points that we have that are inside these boundaries, or the points that are located on the circles, I'm again using another dispatch. And I want to separate them. So I'm again using a pointing curve and using these circles as the input for it. So I'm extracting only one of the circles using list item, and now I'm using pointing curve component, and I define this curve as the curve input and the points as the point input of this for the dispatch for the pointing curve, and then this output of the relations are connected to the patterns of the dispatch. Now if I connect the points container to the A and B, you can see that they are dispatched. Now we can separate them also as the anchor. So I use one anchor only for these points of the first circle, and I define how much they should be moved, or the target points, target location for them. And I copy the same for the second input of the points, so the points that are located on the second circle. So make sure that the same points are connected to the point input and to the move, so that they have the same characters. So now you can see that they are working independently. We can change the placement of the points for the first circle and the second one independent from each other. So this was the first input of how we can define our fabric structure. But as you see, they are not they only can go up and down, and it's not possible to orient them or rotate them. To solve this, we are going to make another definition. So I'm getting this initial part of the code, I'm copying it. Make sure to deselect the group, otherwise it makes a little problem. And also copying the last part of the code, so initially the solver and the goals defined for it. Now by clicking on the input of each of these components, I'm disconnecting them from the code above. Okay, now we can disable or hide the initial code and only focus on the second one. So as you see here, we have also the circles, the mesh, and we want to change how they are possible to be modified. So basically their rotation. For doing so, I'm using a point polar, so that I can rotate the point in space. Now I can put it on degrees for x, y, and z directions, and also define an offset of how much this point should have a distance from the initial plane, which was x, y in this case. So I put it on 5 and define the angles for the z and for x, y directions. And now to see how it works, we can connect it to a line component. So the input of this A would be the point polar, and the B is the points that are generated on the surface. And as you see, this is the line, how it looks like. Now we can also change the XY degree to see how it also affects. We can also define two different inputs for the Z, so that they are working in two different directions. So they are also not dependent. Now if I type line STL, I can define one line that starts from this point polar and has a direction of this line. So by connecting a line to a direction, it also works as a vector. And the length for it, I will use a length component to extract the length of this initial line, and then I define this as the length for the line STL. I can also multiply it by 2 so that we extend the curve into other direction as well, so it's not only upside but also going downward. So now we can adjust these angles. We can also define two angles for the XY degree. Now we have this setup ready. Okay, now we need to also develop or generate two circles on top of these curves, so in different parts. So we want to generate these circles on different points on this curve. So that's by using an evaluate curve, I'm extracting points from this initial line STL, and make sure to also reparameterize it so that we can use the 0 to 1 slider for selecting 1 point on this. Again, I can use two of them so that they are independently from each other. One of them can go up and the other one downward. And now I use these points that are evaluated on this curve as the input for the circle. Make sure to use the same numbers for the radius as the initial circles that we generated on the surface. And as you see, they are not aligned to the plane of this curve, and that's because they are only considering the XY plane as their input. To solve this, we are using an adjust plane component and change this initial plane for these circles based on this line STL. So connecting the point input to the point of adjust plane or plane of it, and the end should be connected to the line STL to be adjusted based on these lines. And now you see that our circles are aligned with these curves. Now what we can do is to connect the naked vertices to extract the naked points of this mesh. And so we want to only extract these points that are located on each of these circles. So again, I'm using pointing curve. And using the circles as the input for the curves. So typing pointing curve, we select or connect the point input to the point of pointing curve, and the curves are defined as these two circles that we defined or draw on the surface. Make sure to also graph this input because we want them to be considered separately. And now we use a dispatch component and connect this point to the list input and the pattern to the P. And you can see that now we have this A input, A output of the points, and they're considering if they are located on each of these curves or each of these circles. Now to know what is the relevance of these points on these circles, so basically what is the t-value of them, we connect the curve closest point and connect the point input to the points and these circles to the curve input. And again here we should graph the curves so that they are considered separately. And now we got this t-value of where these points are located on these circles. Now to exactly find the same points on these generated circles that are moved, we can use an evaluate curve, and again here we should make sure to graph the input for curve, and the t-values are also generating the points on the moved circles. Now to check if everything is right, we connect the line component connecting the output of the evaluated curve points and also the closest curve closest points. There is a mistake because they are 180 degrees rotated, So to solve this, we go back to this adjust plane, and for the n input, we can right click on the n input, and in the expression press -x. So now you see that the lines are correct. So that was just for checking. We can now delete this line component, and now we can go back to the setup of the Kangaroo. So connecting the mesh to the show, also to the edge lengths to equalize the lengths of the mesh and smoothen the mesh. Now we need to define the anchors. So first, so we can extract these outer points which are on the rectangle, and that's again with using pointing curves similar to previous example. So I connect the points to the point input and the curve to the initial rectangle that we draw. And now if I connect the dispatch to the outputs, you can see that I can connect the points to the list and the relation to the pattern. If I connect the point container to the output of A, okay, now all of them are selected because we didn't define a relation or what we are aiming for as the input of our dispatch. So as you see again here, we are searching for if they are just have a coincidence with the curve. So I'm using again a equality function and define 1 as the B, which is we want to check if they are having a coincidence with this curve or not. And now we could extract these points on the rectangle. So I'm defining them as the anchors that they should be fixed in their place. I don't want to define a target point or a move destination for them. But then for these points on the circles, I should define them as to be moved into these evaluate curve points. So I define these points as the input for the points, and the targets are defined as the output of this evaluate curve. And now if I run, you can see that it's working perfectly. So now we can adjust these number sliders, and that's defining how these circles are rotated in space, which direction they're facing to. And also we can define where on these perpendicular curves they are located on. So are they considering on top of the curve or below it or in the middle? So that can be adjusted. Okay, now that we have our setup, we can just simply disable the running options, and we can add more circles, so changing the inputs. Okay, now we want only to see these initial circles, and I can add another empty slider to add another circle. Again, pressing shift to catch all these inputs of empty sliders, and now I can change where it's located. So basically, again, this is the parametric design. We can change everything in the steps, so it's only important that the setup or the process is correct. Now I can also add another radius for the third circle. Make sure also add it to the circles of the moved circles, and now we can also check these lines and how they are rotated in space. So we can also add another degree specifically for this third circle and how it's rotated based on this curve. Okay, now it seems to be fine. But overall, all these sliders can be checked out afterwards to reach different structural forms. So we can also add one t-value for where this third circle is located on this initial curves that or lines that we draw for it. And as you see, everything is remaining the same. So the circles are all aligned to the curve. And now we can enable the mesh and see what will be the result. So if I make the boolean true and reset it, you can see that everything is updated. So again, we can change the number sliders to reach different results. Now that everything is done, I can just press false, so the setup is not changing anymore, and I can connect the mesh to the output of this list item. I can also right click and press internalize the mesh so that it's not dependent to the definition anymore, so it's something separate. And now I'm using a mesh curvature component and plugin to analyze what is the mesh or what is the curvature of this generated mesh. And in the curvature type, we can define what we want to extract. For example, if I right click and put the set integer as 2, you can see that it just shows the Gaussian curvature, and if I change it to number 3, I can see the mean curvature. That's important for considering or checking if this generated surface is really a minimal surface or not. And to check that, I can connect a panel to the output of these values, and you see what are the numbers, so they should be as less as possible. And also to check them easier, I can connect a min max component. You can find it in the Heteropetra plugin, and install it and check these outputs. And for doing that, I should also flatten the input for this min max component, and by connecting a panel to the outputs of min and max, I can see what are the range of our numbers. So basically, this generated surface has a mean curvature of between these two numbers here. So then I can also define it as alternative 1, and then go back and check and change the direction of the lines, also where the circles are located, to reach a mean, to reach another result that has a mesh where the mean curvature is more close to 0. That's it, and thanks for watching.